Right. So I want us to look at this concept of uh, RF signals. I decided to do the video because of the question that one of my listeners asked me just to give an insight into it and the relevance. Normally, if you look at a typical wave, you have you have because wave is a disturbance, so you have the up and down of it, and here you have your crest as it is called, and here becomes your trough. So by convention, this side is supposed to be the positive signal, and this is supposed to be the negative signal. In reality, if you look at the sound wave, the amplitude is not maintained at a constant value. So as the sound comes, the amplitude will be dropping over time until it dies off. So this is one pulse. So if I have a pulse, if I have a probe now, let's say this is Marango probe, for example. If it's producing an ultrasound, it's producing as a pulse. So, and so this is one pulse. It releases another one and dies down another pulse. So that's what it happens. The distance between the beginning of this pulse to the end of this pulse is usually what we call the pulse width. So how do you get the pulse width? It's a very simple calculation. If because if you count it, this is one wavelength. This is the second wavelength. So if we go by that, this is 1, 2, 3, 4, 5, 6. So which means the pulse width is 6 wavelengths. Wavelength is represented by lambda. Pulse width is 6 wavelengths. This is the basic calculation. And you know that your velocity is f lambda. So if you make wavelength the formula, you can put this all into this and your pulse rate becomes the number of wavelengths multiplied by velocity over frequency. We normally don't use wavelength in calculation because we cannot easily get the value. But if I pick this probe, I can get the frequency of it from the is normally written on the probe. The velocity of the material I'm used to work with, I can easily get it. So if I know the number of wavelengths as it is, I can get the pulse width. But when we represent this sound beam or sound wave in our material, we normally will decide to tell ourselves, are we going to be using a half wave or are we using what we call the full wave or what we call the R wave? So this is half wave, half wave. This is full wave and this is the RF. RF is called the radio frequency. So the representation, if you are picking just this top side of it, that is your half wave positive. If you are picking this other side of it, it becomes your half wave, negative. So inside your half wave, you have your half wave positive and you have your half wave negative. Then you have your full wave. In the case of your full wave, we are taking both the top and the bottom together. That is your full wave representation. If you are taking your radio frequency, you are looking at the sound waves in that form where it decays, where it loses its amplitude as you go on. So in that case, the machine represents it in this form. Now, if we want to illustrate and check this whole half full wave how it is applied and how you see the representation in the unit. If you go to your menu in the, we are using this Sonatex D70. If we go to our calibration menu, which is cal, if we go to our cal menu now, under our amplifier, you have your frequency range, then you have what we call detect. So what do you want to detect? This is where you have the opportunity to pick between, if you are doing half wave positive. So this end is our half wave positive. What the sound basically does, it will aggregate and represent only the positive part of the wave. So let's say we choose half wave positive. So we'll go to half wave positive. This is half wave positive. If you look at it, you observe this mark. You observe this mark there. You see these tick spots there. If I go to the same menu and I go half wave negative, you still see it there at different points. This you are not going to see if you take full wave. So let's look at full wave. You can look at it, you see that time you are seeing there is not there. So when you do half wave positive, half wave negative, you always see that tick out there, which tells you are not doing full rectification. Now, if we look at the last option, RF, which is the radio frequency. So if you look at it, you will see this is a very unique representation. You see, like I told you, instead of seeing this multiple backward, you are going to be seeing this representation with decaying or damping strand signal. So this is an ACE, an RF representation. You'll find it in most flow detectors. You have the opportunity to set it this way. Some people find it difficult to interpret, but the RF signal sometimes even gives a much more cleaner representation. You can easily differentiate between one echo and the other. And if you have a scenario where you have echo that are close together, if I have where are we? I'm getting locked. Okay, I have something like this. I have something like this. This is no the material, the attenuation is large, so damping signal. So if you look at it, you can clearly differentiate. You see that this is one signal, this is one signal, this is one signal, this is one signal, this is one signal. You can see how they are clearly differentiated. But compared to your full wave, let's go back to the full wave again. So if we compare this ROF for, now let's see the ROF for this versus the full wave rectification. So some personnel are more comfortable with this because the signals are clearly defined out compared with if I go back and I take the RF. If you look at it now, if you compare it with the RF, you can see. So personnel are sometimes not so comfortable with the signal that is coming out from the RF. So where is it relevant? When do you need to use it? In TOFD, the signals are usually represented in the form of RF. So if you are very comfortable with reading RF signals like this in your conventional UT, it's very easy for you to interpret when you do TOFD. Then there are specific inspection rather, where the owner or the client will request that your signal should be presented in the RF. So you should be able to differentiate and interpret it. It's still simple. If I get it like every other signal, by the time you get it, it's the same results it will give to you. If it's a properly calibrated unit. If I go to my gate, it is still the same process like others. If I say my gate starts, if you see, it's still the same thing. For this V1 block, you see, it's still the same thing. Nothing changes. Still gives you the same reading. Every other thing is the same. The only difference is just the representation. So I believe that helps. Thank you.